And hello everyone, thanks for coming. This is my first time come to RuCon and share some topic. And today we are going to share a topic about our off-time project, side project about like how do we make OT adversary emulation. So we quickly go through ourselves. I'm Vic Huang and I'm from the UCC Hacker, which is a technical community from Taiwan. And this is Sol Yang. He's also an independent researcher. And today we're going to share the first part. I will share the first part, and he will share the second part. And this is our outline. First, we'll quickly go through the introductions, and then we will share what is the adversary emulation. And we want to build an adversary emulation tool, so we have to review and analyze and try to reproduce an attack from the malwares. And then we are going to extend the attack. And then in the last part, we will have a demo that we attack the real devices. Okay, let's start. So what is ICS? It's an industrial control system which is used for control and monitor the industrial process. And in ICS, there are two important parts. The first part is DCS. Maybe it's in your right-hand side. It's focused on the fine control, and it has the different control room for controller. And it's used customized control protocols. And most of them are private protocols. And different vendors may have different protocols. And for SCADA, which you may have heard about it, and also PLC, is kind of focused on remote control, and it's programmable. And so you can do some develop on yourself about the public control protocols. And those protocols, you can find the spec on Google. So most of our security research is focused on SCADA, include the research we have. And then what is IT and OT? People use a Purdue model to describe IT and OT, and they are 5 layers. And for layer 5 and level 4, they are enterprise level, which is known as IT domain. And there's a DMZ zone to separate IT domain and level 3 below, which is the OT domain. And in OT domain, there are still some Windows devices, but the more important is they may have some controllers like PLC. And in the bottom of the lowest level is sensor and actuator. They have some signal data, and then will transfer the signal data to the digital data for some programming or some education. And then, what is adversary emulation? So this is MITRE, ATT, and CK ICS matrix. And similar to the ATT and CK matrix is described the attack pattern and different kind of attack. So this is kind of whole map you can use. And in this kind of matrix, it's used a TTP mechanism, or you can say architectures, that the highest level is the tactics, which describe the target of this execution, and then the details procedure, which kind of the models or attack technique that to achieve the tactics. So how to use the ATT and CK matrix is that you can put the known threat. This means some APT attacks or malwares, and mapping on that matrix, and then to do some tests. And so you can use the known threat skills to test your own environment. For example, the factories in your enterprise, that to find that the environment is vulnerable to those known attacks. And for adversary emulation tools, it's as known as the BAS, Bridging Attack Simulation. And also different from the attack framework like Metasploit and ISF, it's more like creating more single models, and you have to decide how to use it. The adversary emulation is focused more on automating. So it means it tries to reduce the human decision in the whole attacking process. And then we found some tools that is also commercial and open source. But most of them are focused on IT domain, especially Windows. And just few focus on OT domain. But I think last month, the MITRE just released a Caldera OT, which is also focused on OT domain, but they just provide few attack model. So if we want to build the adversary emulation tools, we have to know about the known threats, which is the ICS malware divided by MITRE. So we have a research on those malware. And this is the ICS malware overview from 2010 to 2020. And you can see there's over 20 malwares defined by MITRE. And from the famous one, the Stuxnet, to the latest industrial, which is focused on attacking Oakland factories. They are different kind of malwares. And we self-defined it as 4 different generations of malware. In the first generation from 2011, they focus on data steal. They try to sniff and steal the data from the factory or the industrial place. And then start from 2015, it becomes more modular design. It supports more different protocol attack, especially in the industrial. And also there are PLC blaster, which is shared in Black Hat, that's abusing the PLC proxy to attack a network connection between PLC. And also there are classic malware named Triton, which is fully focused on the Trisis protocol that is used in the electric factory. And then the third generation is ransomware. There's a lot of ransomware appeared after 2017, which is WannaCry or others. So they focus on trying to equip the old Windows devices in your environment. And then since 2022, it's become more complexity. The malware is become some thief try to put a lot of toolkits in his backpack and try to break into your house. So now they have more flexibility and more different protocols that they can attack. So the trend of ICS malware development on the protocols is from the single protocols to the modular design and multiple protocols. And we have a quick summary for those malwares. They have 2 main targets that they may want to do some information collections, and also they try to break the factory or field operation. And there are 3 kinds of malwares. The first is a worm-like malware, which focus on spreading and sniffing. And the second one is ransomware. And it focuses on attacking IT devices or the Windows devices in OT. And that's one is the toolkits, which can support a lot of, to attack different protocols or multiple protocols. And also, we want to share what we found in review these malwares. The first one is only some of the malware really attack the devices like PLC and IED. The rest of them just focus on the old Windows systems. And also, we found that there's some hard code target IP address, especially its internal IP address, and also the tag name information. Tag name is a kind of object in some protocols that it will represent some data. You can put some data inside the tag. So it's like super strange if the malware knows like which IP address or which tag is going to attack or abuse. And also, PLC normally has 3 modes that some of the devices have user to physically touch the button to change the mode. They have like rarely 3 kind of mode, run-only mode, programmable mode, and hybrid mode. So maybe some of internet happen is because they have the misconfiguration. And then the last one is about the PLC proxy. That is kind of PLC abusing the connection between 2 PLCs. But normally in the factory, the HMI, human interface, and PLC will be deployed one-to-one. So it's hard to like abuse kind of connection between PLC. And then, as we mentioned, we focus on OT and protocols. So we select the 6 malwares that are targeting OT, and then we summarize it as a 4-stage. And not every malware have these 4 stages, but some of them just achieve like 4 stages. The discovery, collection, manipulation, and check-in invasion. And for this 4 stages, they have 2 main targets, which is manipulate the data or try to abuse the control. For the control part, because sometimes they just send the normal command or instructions. It's on spec, but it just try to abuse this kind of command to make the device break the operation. So it's still some kind of abuse, but it sends a normal instruction. And another kind of like a control attack is it use the by design vulnerabilities like CVEs to damage the devices. And for data target, they just try to make data error, and then maybe some protective action may be triggered because the weird data. And also, normally in the factory, they will always trust the data from the lower level, so it's a good target to attack. And then for first stages, discovery, for example, for data targets, Triton has tried to broadcast the specific packets and wait for a certain response. So if the device's response, and the malware will know, oh, there is a target devices in the network that I can reach. And then for control, if you have used a map to do like mobile device scanning, you will find it's using the official function code 17 to try to scan the network and find if there's something respond or from some IP. So, and also the function code 42 is also available for scanning. And in the stage 2, like a lot of malwares try to sniff and to enumerate the different texts and collect the information and waiting for the next step. Okay, so the most important part is the manipulation stage. For data targets, you can try to ruin the data in the HMI, or try to put some strange data to trigger the protective actions that's right in the POC diagram. And for control targets, like they can just use the different protocols, try to abuse the devices. And there's a fun part in the last stages, that because some of the malware try to write a meaningless code to overwrite the written malicious code that's uploaded to the devices. So they try to don't let the forensic to find out the malicious code. And also, after he uploads the malicious code and the devices run the malicious code, you will try to detect the mode that POC did held down or is running, to make sure that the malicious action is work. So this is the quick summary of 4 stages. And we use these 4 stages to create our own tools for fun and profit. And somebody may know there's a lot of different POCs, and they are using different protocols. This is the Cheers for Rukon.
For the best shit.
Wow, didn't expect that. And then, let's continue. So our design core is, we can use that 4 stages to reconstruct and reproduce the malware detection, and also extend the malware detection. And if you have tried to download and use some POC under GitHub, you may find that the POC they write is not work on your environment. And if that happens, you have to debug yourself. But they just write from start to end the whole attack process in one code. So it means you have to read all the code and try to find out where's the bug. Sometimes it just doesn't work. So we separate the one attack process from the malware to different steps, and you can combine it by yourself like toy bricks. And also, we are not expert in IT attacks, so we want to find a way that you can combine your IT attack by yourself and also using the OT attack provided by us. So the general purpose is that you can use this tool to test your defense solutions. And also this tool is mapping to ICS matrix, so it's easy for understanding what happened. So we picked the Caldera, which is developed and released by MITRE, and we built a plugin with 10 protocols and 23 techniques that we reconstruct the attack in Python. And it's important because a lot of different POC, and they are written in different programming languages, so we just move it to Python and to extend the attack. So this is an example that we make for the famous malware traces. We start from detect the internet and the network, and then we will send the malicious packets and to detect the operation mode is changed or not, and then upload the malicious program to POC, and then to check if the POC work, And then to run the malicious code, the final step is to upload the trash code to the POC to overwrite the malicious code that we have. And then in the next part, we'll show the demo videos and how we extend this attack in the different protocols and try to reconstruct that attack. So here we are going to introduce the second speakers. So he will introduce the rest of parts. Please give me a pause.
Next, we will introduce who is Caldera cake we have done. One is IEC-61A50, and the other is MITRE. And we will play demo video and color explanation. And the first one we will talk about is IEC-61A50. It is a standard used in the electrical environment and have a 3 protocols in this standard. One is NS protocol, used to control the device. Another is SV protocol, used to measure the device value. And the other is Goose protocol, used to pass the event between ID device. And here we take Goose as an example. It is a protocol for broadcasting event. When no new event comes out, the old event will be broadcast all the time, and will let the value of SQ9 increase. When new event happen, SQ9 will recycle 0, and SQ9 will increase. What we want to do here is to sniff and fake these two values. This is the structural diagram of Goose friend, because we want to fake values of SQ9 and SQ9. So we need to know its position in the Goose PDU on the right side of the slide. Goose will put some information in all data. We also need to know this information, but we may not know the meaning of all data content. This requires pre-analysis to understand, but we know that Goose passes where the event happened or not, and use the Boolean values to display. So we can simply by sniffing the traffic for a period of time and flipping the content of the Boolean values. In our past practical experience, triggering an alarm will indirectly trigger the control of upstream device, because in general, the factory will do some control to handle its sessions. So we can indirectly affect the operation of the factory by triggering an alarm. And this is the attack flow that we will show later in our demo video.
Can we switch the? No.
卡张哦，有出来。诶，这个影片可以出来。
We try to play a videos.
Yeah, video 那个好风。这样。是要按哪一个？是。
Seems it's not working. 就是它延伸桌面。
哦，延伸桌面。哦，看一下。有吗？
Sorry, we are trying to figure out how can we play the videos in the screen.
Here is our IC-6185 case bay. On the left side is Kali, used to attack device. And on the right side is HNI, and in the middle is our device, used to simulate the IC-6185. And now we start our adversary emulation. First, we want to sniff the package and want to find good package. And we will record the SQ none and SQ none. And we want to flip the content and let it send the alarm. And we can see in the left side, it has cup, middle, and button. And in the device in the middle, you can see it display red. It means that it has alarm. And now we can see device in the button, it display red. So our attack machine send the alarm. And we go back to see the Kali. It kills us that it finish our adversary emulation. And we go back to see the case bay. We can see we let this device turn on. We don't send any control package. We just let the device to handle the exception and indirectly let the upstream device do some abnormal operation. And now we introduce another case bay. It is Mitsubishi's electric device. On the right side of the slide is the product diagram of the official website. From left to right, the product functions are the least to the most complete. We use the IQ-R series on the far right as the device we case. And the ICS protocol used by the device is MITRE. And here we use MITRE to briefly introduce the process of our general analysis of ICS protocol. First, we will read the official user manual, and then map the functions of each field to the technique defined by MITRE attack ICS. Generally, we will focus on two parts. One is how to identify the ICS protocol, which is the green part of the slide. And the other is how to use the function of the ICS protocol to control the device, which is the yellow part of the slide. And the reference here is the yellow part we mentioned on the previous page. There will be three parts. One is function call of the protocol. Another is device address. And the other is data to path. What I want to explain here is the difficulty we have in building automation, because the device address will be different according to the case-based environment. So in general, we can only enumerate all possible failures and have no way of knowing what will happen after an attack. So for the convenience of demo, we have a pre-analyzed protocol and know which failure represents which device address. Therefore, we can do a good job in the attack script directly. This is like most ICS security incidents that have happened in the past. Some incidents, hacker can precisely attack what they want to attack. So it means that the hacker knows specific information in advance. But if you stand from the point of the view of automation, under the condition that you don't know anything, you have to enumerate all the failures to test. It is also difficult to know what will happen after an attack. And here we will go through the famous ICS security incidents that happened in the past, which named Stuxnet. We choose to use Stuxnet because it is a common attack chain on ICS security incidents. Its main attack process is first to find cookie, and then check version and rewrite device value, and finally do some control and let device abnormal. So here is our attack chain for MITRE, and we will show the demo video. And this is our MILSEC case bay. On the right side is device and POC. On the left side is HNI. And now we start our adversary emulation. We first will scan local network and want to know POC and HNI's IP address. And each can, when we find a car key, our Caldera will record their IP address. And now we want to check POC type. And here we know POC type is IQ-R series because different type of Mitsubishi's device use different PEGI formats. And now we want to read device address value. And we will record these values. And here we want to change SV value. SV value is the upper limit of device pressure. SV value is the upper limit of device pressure. If we change this value, we can let the device pressure value over the upper limit and let the device broken. So now we change the SV value. We can see we let it from 2.93 be 6.72. And next, we want to open the air compressor. When air compressor open, it will let the pressure value start to rise. We can see it display red. It means that air compressor open. So now we go to see the case bay. We can see now device pressure value is 0.6, and it will start to rise. And when it over the upper limit, the device will broken. So finally, we want to call about our opinion on the use of such tools by company. We believe that no matter what emulator you use, there are basically three kinds of attack. One is CVE, another is use some way to let device cannot control, and the other is use ICS protocol function to do some abnormal operation. And when you want to use automatic attacks, it is hard to know what impact it will have on the factory. So we think maybe you can use digital queen as the clone of the factory. Though digital queens are still many challenges, we think it will be a trend in the future. And here is the summary of our speech. First, we call about background knowledge of ICS and adversary emulation. Then we summarize the behavior of ICS malware in the past 10 years. We then propose 4 stages of its behavior, and from data and control, these 2 parts point of the view to explain. We then propose this case using 10 different ICS protocols and using IEC-6150 MILSEC to demo automatic case. Finally, we talk about our views on the use of this type of tools by enterprise. Thank you.